I'm going to talk about clickbait title, SRE's crystal ball. If there was ever a time to throw some equations at you and make you think, that was probably right after the coffee break. So I hope as the caffeine kicks in, I can stimulate your thoughts a little bit after. So without further ado, I am Aravindh Sampathkumar. I work as a site reliability engineer at booking.com. I have a background in high-performance computing clusters, working with storage systems as a performance engineer, and generally from performance engineering from computer science background. That's a little bit where I'm coming from. Today, I wanted to begin with a big caveat. This is like a big picture. I don't expect that you read all the miniature text. That was intentional. We have three big fields in themselves: performance engineering, site reliability engineering, and queuing theory, with a lot of things in those fields. There is no way I'm going to cover all of those topics in the 35 minutes around here. So my goal is the thing in the middle, with a few handful of topics: golden signals that you would all be aware of, capacity planning, thinking in Little's Law, and USL. So this is just to tell you that the scope I'm consciously narrowing down to this. Again, a little bit of a big picture. I'm thinking before throwing a lot of stuff at you, the goal is to just have some fun. I'm going to share what a small subsection of all of these three major fields. So we can take it further along in the questions in whichever dimensions as it becomes interesting. The goal of my topic, goal of me choosing this topic, is to inspire my peer practitioners, you all, to listen to this talk and apply these concepts in your daily job or in your home labs or somewhere in ways that I haven't thought of yet, and that means I succeeded. One of the things that I would like to bring up that was thought-provoking to me was in one of my previous jobs. I had a mentor who made me think this way. Any system is a chain of bottlenecks. So it's the fun exercise. At some point, somebody thought it was acceptable performance. Then you inherit the system, and you realize there is somewhere there is a bottleneck, and then you work on it and you improve it to an acceptable level to you. That just meant you have proceeded to find the next bottleneck that you have chosen to live with. And then a few years later, someone else, even more enthusiastic than you are, solves that bottleneck only to reveal the next. So that's the rules of the game that we play, and that's how we approach things. And that has always been in my mind, to think that this is what I'm choosing to live with, because at some point you have to stop. All right, so more caveats before I begin. Credits, I keep referring to USLs, and it stands for Universal Scalability Law. It was authored by this person, Dr. Neil J. Gunther. I've sat through his workshop on this topic. We have sped through it for 4 days. This is a very nice workshop, which you can look up after the talk. And some of the pieces that I'm going to demo is maintained by another person, Stefan Mudding. And lastly, another ex-colleague of mine, Phil Larson. He is a mathematician, performance engineer, who has inspired me to apply queuing theory in places when I was a junior engineer. Just wanted to highlight how important it is to mentor somebody, and maybe they will talk about this stuff even after 10 years. So that's some credits. So why do we bother? Why think about queuing theory? Why go through this pain? I assume in the audience, many are site reliability engineers, and we all deal with SLOs. We have our SLOs, then why bother? SLOs are reactive in nature. We always answer the question, are we failing now? Are we doing bad now? Are we slow now? And the idea is to move or transition from that state to, if traffic increases by X%, would the SLOs breach? By what? And will adding resources in this place help or hurt? These are the kind of questions that I'm hoping I will equip you all to think about an answer. We are moving from firefights to actually preventing some of the issues. We all know if I said all issues that I would just be lying. So here's the agenda. First, I'm going to spend a little time setting the baseline, help everybody get in the common terminology, thinking in queues. So I'm going to get to a little bit of basics on queues. If somebody sat through the topic in the morning from another person, speaker from GitHub, he already touched a little on Little's law and everything. I promise I'm going to show you a slightly different interpretation of Little's law from practical aspects as well. And then we are all familiar with golden signals. I'm just going to map it to some of the queuing terminology that we're going to look up. And thirdly, I'm going to spend a little time on describing Universal Scalability Law in practical terms. And finally, I've prepared a bit of a demo with some contrived example that I'm hoping would highlight the specific applicability of USL. So that's my plan for the next minutes. Very, very, very quick introduction to queuing theory. A Danish guy, A.K. Erlang, figured out or formulated queuing theory when he was tasked to compute how many circuits, during the circuit switching era, how many circuits he needed to have tolerable waiting times. So that's where it all began. And to think about it, queues are everywhere. It's in load balancers, connection pools, Jira boards, and also here, just outside, when you want to take the escalator down. Nobody likes waiting. The reason why queues are interesting is, and why we have to talk about it at conferences, is queues are non-linear in nature, and it's by definition not intuitive for us in the way we think. So double the instance count and double the capacity, and you can serve double the load, right? Double the load, right? So everybody sort of intuitively thinks that way, and by now, whoever has spent a little time in their career knows that it's just not true. We need to find a way to quantify that. And queues occur even if there is enough average capacity. So when we think of how much resources do we need to provision, we often think in averages, and that can be a pitfall. Think of a grocery store. In a busy day, we have grocery lines, and if there is variance in arrivals, that leads to queues build up. So if you start thinking in that terms, then you understand how variance is a problem. And the same with high variance in service times. If you have one worker who likes to chit-chat with a lot of people that are in the line, then we have a problem. So to set the baseline for the rest of the talk, while I'm going to throw terms like arrival rate or L lambda and whatever, I would like for you to picture a very basic queue so that we are all in the same line with terminology. So we have an arrival, we have arrival process, determines what is the distribution of arrivals, and arrival rate is the rate of arrival of the requests, and we have a queue. It's important to notice and remember queue discipline, first in, first out, last in, first out, and the important terminology that I will be using in the subsequent slides. We have service time, is the amount of time a server is doing the work, and queue length is the number of requests waiting in the queue, and wait time is the amount of time a request spends in the queue. And importantly, residence time, response time, or latency is the sum of amount of time spent waiting plus the amount of time actually doing the work. So with this queuing terminology, I just put that down on a neat little table for somebody who is looking at the presentation after. There's one extra thing here that I didn't talk about in the thing. It's the utilization. Rho is the fraction of the time a server is busy. So with these, I'm going to try to map the golden signals that we all look for in queuing theory terms. So latency is service time plus waiting time, as I said. Utilization of the server drives the waiting time. So the harder you push the server, the higher the probability of your requests waiting. It sounds intuitive, but you will see why I wrote it here in the next slides. As a leading indicator of this problem, you could always consider coefficient of variation. So when you think of coefficient of variation, it helps you understand, for example, average latency, and if the latency is always around the average, then you're not going to have a problem. But if you have the same average, but one request was much shorter while the other one was much bigger, then you have problem in your hands. That's why coefficient of variation is always a good leading indicator. And traffic, as we look out for, it will be termed as arrival rate, which is the demand for the system. Some of the errors are symptoms of system overload, and saturation is as high utilization as such. So the golden signals approximately maps to how we're going to talk about from the rest. So I'm going to breeze through Little's law a bit because someone else already talked about it, but it's important to understand this as a law, more like the law of thermodynamics. It just applies. So if you see numbers that don't conform to this law, then you got the numbers wrong. So it's important to keep this in mind. A very, very useful law to perform napkin math, which I'm sure we all do. So L equals lambda R. L is the number of requests in the system. Lambda is the arrival rate, and R is the response time. Sounds very simple. I know the equation is not what we want to see and keep on the mind, so I thought I would nail this down with an example, which is 2 slides away. So the famous hockey stick curve. I don't know if everybody got a chance to see this, so I'm just going to quickly walk through it. As the idea is very simple, right? So as utilization of the server increases, as you go farther to the right, the response time you expect to increase, which is kind of intuitive. The goal is to operate at this point where your response time starts to increase, but not as fast as before. So at low utilization, your response time is completely composed of service time. Your requests are not waiting. And when you get to this part, what we call as knee in the queuing theory world, is where your response time starts to spike up at a hyperbolic nature. So you ideally want to operate your systems here, because if you're operating here, it means you're leaving resources idle and you're leaving money on the table and your boss is not happy. And if you're operating here, your boss is again not happy because, well, your SLOs are all in red. So ideally, you want to be here. But the fun part is figuring out how to be there. So that's what we are going to figure out in the rest of the session. A little intuition before we get into applying Little's law. It's very easy to think about, right? We have 3 servers. We attach a queue for each of them because queues are fun. You can attach to everything. And there is also another design where you have 3 servers emptying from a singular queue. Which do we think would be better generally? I'm not going to be able to listen to your answer, so I'm just going to blurt it out. It's this, because we saw that variance in arrivals and service time is the problem. By choosing this, we are allowing the variance to come down. None of the servers are waiting for the request to come in. In this case, the first 2 are, even though they are busy, the other ones are queuing up behind while there is another one twiddling its thumbs. So with that, I wanted to show you a simple example of how one of the ways of applying Little's law, so it kind of stays in your head. We have a API endpoint that's timing out. Latency has spiked, and someone's paged, and they're looking at a few things. So they have listened to queuing theory somewhere, so they are going to look at arrival rate is 180 requests per second, traffic. Average service time for that at that moment for the service is 50 milliseconds per request. Number of servers is 4 server pods. I specifically chose API server pods because servers can be anything. It can be bare metal servers, VMs, Kubernetes pods, or processes or threads. Whatever is actually doing the work is termed servers for the context of our talk. Then they are wondering during the firefighting call that should we scale it up to 8 pods? 8, 9, 10, 12, what do we do? And then the next question comes up, why 8? Would it be enough? So that's where the napkin math comes in. And that little simple equation that we looked at before. Utilization is arrival rate times service time by number of servers. You can just pull out a napkin and start to plug in the numbers, and you arrive at this utilization of 2.25. This is a number that shouldn't go above 1. Utilization of 1 means it's a stable system where the number of requests coming in have been served in a stable system. If this number goes above 1, it implies queuing. The requests are waiting, and the queue is going to grow indefinitely. So the goal is to change this number from 2.25 to something below 1. So further moving in the question, somebody asked, should we scale it to 8 pods? So apply that number in there. If you change the number of servers to 8, then the utilization becomes 1.125. So the answer to that question is, nah, if you do that, you're still going to be paged in a little bit. So let's increase it to 10 pods, because then the utilization will come down to 0.9. Why 0.9 instead of aiming exactly 1? Because remember, there is variance. Always account for variance. That's the villain that increases queue. So this is a simple way of comprehending Little's law and actually using it in real life. So with that, I made a clickbait title of crystal ball. So I need to show some predictions. So I'm going to go to Universal Scalability Law. Before we describe the equation of Universal Scalability Law, what is scalability? It's a mathematical function of being able to perform more work represented as requests per second or transactions per second, depending on the field, while the work per server remains constant and the number of servers increases. I just said in a mathematical form of definition what we normally think about scalability. And that's the formal definition of scalability. It's important to put this down so the assumptions are clearer as we go further. And this is, I did slightly reword it from the way Dr. Gunther had defined it, so I needed to call it out. He might get mad if he sees this. So before we go down the scalability route, basic thing, linear scalability. It's the marketing term. Everybody says, oh, I've got this fancy new database. It's, of course, linearly scalable. Anybody says that, you're going to react with your eyebrows, right? So we all want this, that you add more servers, the amount of work that they can do linearly increases. Talks over, we all go back. But unfortunately, that just doesn't happen almost any time. To represent this ideal condition, I'm just going to say x of n, which is throughput of the number of servers, is gamma times n. Gamma is the ideal single server throughput, and n is the number of servers. So think about it as number of servers times one server's throughput. So very easy, but it helps to interpret it as this equation. And there is a reason why I put the 1 in the denominator, because that's anything in the denominator is inversely proportional to the throughput. So we're going to see what can make this condition not right. So villain number 1 enters the picture. Contention. So what is contention? Contention is when, say, imagine lock contention. You have all these requests that are waiting behind a lock waiting to obtain a lock to write to a database. They are waiting for some shared resource. They're waiting to write to a shared map. So, which means they are waiting by definition, and the system can't give you that ideal throughput. So your curve starts to look like this, with number of servers on the x-axis and throughput on the y-axis. Your throughput slope starts to change because of that contention parameter. And we are going to codify that in the equation as the alpha parameter, and that's on the denominator with an order of n. So as the penalty increases, the number of times of the number of servers you have. So it's helpful to think about contention penalty is linear with the number of servers. Enter villain number 2, coherency or crosstalk penalty. So it's helpful to see both of them in the picture at the same time. Coherency is, or crosstalk implies your requests that are currently in flight. Let's say you have 64 requests in flight at that moment. They need to coordinate with each other to get stuff done. Now, coordinate is a bad word for performance in this case, because coordinate means they have one-to-one. In Universal Scalability Law, they assume one-to-one coordination. That's a n square. So every request needs to coordinate with every other request in the system. And that's why this has a very severe penalty and does something really funny. It causes retrograde throughput. So the more requests that are in the system, it starts to affect throughput worse, and then you start to see throughput go down, which means the more servers you add, you are actually going to get worse performance than you began with. And this is actually real, and it does happen. I've been told from tribal wisdom, somebody told me about earlier MySQL versions, that actually if you upgrade it from a 4-core box to an 8-core box, the performance actually went down. So this has also happened in the real world, and this is a penalty to represent coherency or crosstalk. And how do we represent that in the equation? It's this way. And as you see, it's every node, every server needs to talk with every other server, so it is a quadratic penalty. And you see this, even a small value of beta is going to show up as a big penalty on the throughput, which is what we care about at the beginning. So this is the Universal Scalability Law. Gamma represents ideal single server throughput, alpha represents contention penalty, beta represents coherency penalty. So now that we have seen the equation, now that we have understood the two coefficients that we care about, what do we do with it? The goal is to model system scalability, of course. We observe the system behavior and identify the metrics from our system and estimate alpha, beta, and gamma from our data using nonlinear least squares regression. And once you know these values, now you know what the values represent in terms of alpha and beta. So you interpret it as, okay, I'm losing performance because of this penalty or that penalty. Now what am I going to do with it? That's the idea. So with that, I would switch over to show you, once my computer allows me. I prepared a small representative program to test this and show you, bring up some numbers and show you. So this is a simple Rust program, a single file that has 4 endpoints: /work, /contention, coherence, and summary. Each endpoint is meant to exercise one particular penalty. Work is the linear workload. Contention is with a shared resource, so requests are contending for something. And /coherence is that quadratic penalty where the requests need to talk to each other to figure something out. So fundamentally, what it does is it has a compute-bound workload. It's just doing some bitwise arithmetic, which is not something that the compiler should optimize away. So it really costs CPU time. And this is how the work handler looks. It just performs that work with the X number of iterations. And the contention handler looks like this. It also does the same work. However, now I've added a little bit of sleep time before, and then perform the DB work, and then do the sleep time again. This is to sort of emulate the idea that you have to do some work, but you also have to persist that state and then continue to do that work, if you can imagine it to a real-life scenario. And then comes the coherence handler, which is, if you think about it, it's a penalty. So I'm adding this as n times n minus 1, just like in the formula. I'm tracking the number of in-flight requests. So at any point in time when the test runs, I'm calculating how many requests are currently in flight, and I'm making them quadratic and making a penalty and performing the amount of work according to the penalty. So this is to show you the service time actually increases with the number of requests. So that's the simple program, and I run this program using a setup, using a load generation tool called work, and the goal is to exercise this program with varying levels of concurrency. Now we're going to look at applying USL in 2 different modes. Give me one moment. Yes. So why did I switch to a Colab notebook? I didn't want to run this demo live because it takes time and it's confusing. I ran this load test, but I'm just going to show you what I did. So you can apply this in 2 ways. One, to look at software scalability. What do I mean by that? You keep the hardware constant and push the software part and identify the penalties. So I took that service and I restricted the resources the service has to 32 CPU cores. And then I'm running the benchmark load testing tool to increase the concurrency, just in requests per second, and then seeing what actually happens. So this is how the data looks like from I'm basically obtaining at what concurrency, what throughput do I get, and the goal is to see how it saturates. Yeah. So once you obtain that data, I'm consciously showing you this so that you can replicate this in your own time. You apply the USL model it's an R package written by Stefan, so it's quite easy to just literally plug your data in. This is just a fancy plotting function, and I'm gonna plot this, and this is our ideal condition. A compute-bound load without any other penalties, just literally scales linearly, and alpha is 0, beta is 0, gamma is the ideal single server capability, that's 15. So this is what everybody wants, and we do get and done. So another way of looking at it is through processor efficiency. So the efficiency of adding further processors, or in this case concurrency, adding more concurrency is just nothing. It's the more you add, the more performance you're going to get. So this is the ideal form. And now comes the first impact of the first villain, that is contention. As you see, it starts to increase linearly, and once it starts contending for that shared resource, your throughput starts to plateau, and it just goes down like this. And the way I obtain this plot is that the dots are the actual observed metrics, and the line is the USL fit. So the USL model is saying this is what I expect this to go. So it says alpha is 0.097. It's 9% of the time is spent doing serial work. That's what it should be interpreted as. And beta is close to 0, and gamma is this. Now the same efficiency plot looks like this, which means the more processors you add, the more servers you add, this is the efficiency you get in terms of the result. So which means, in another way of phrasing it is, at this point, for every amount of servers I add, I get very little out of it. This is the plot for the concurrency, for the coherence. And you see beta value is this. Even though it's a small beta value, it has quadratic effect. So when you see it, when you see in combination of alpha is 0, then you kind of know what is going on. Efficiency of it looks like this. That was pushing one piece of software to see where your penalties are. So you have your own service that your team wrote. You want to see what penalties are there to work with. Where is the bottleneck? Am I losing performance on the table because of contention or because of coherency? And now comes another aspect of it as hardware scalability. To answer the question of, I have this service, I want to deploy it, and I want to choose the right amount of servers. How is my service scalable across hardware? If I throw my hardware at it, how is it going to perform, and how is it going to scale? So I made a simple test setup, basically 2 EC2 instances, one having the service, the other one having the test harness, which is the work tool. This one pins the CPUs using the task set command, so it essentially limits how many CPUs the application runs on. And the idea is to iteratively add the number of CPUs available to the service and increase the concurrency according to Little's law and see what actually happens. How does it scale when you add more servers to it, more CPU cores to it? In this case, my servers are CPU cores. So I do the same thing as before. My linear scalability, it's much easier to interpret. I'm adding cores. So the more cores I add, the more throughput I get. The more I can keep on adding more cores, no problem, I will get throughput. For the log contention, it's the same this way. My alpha value is high. I spend some time serialized. So I'm not, the more, after this point, if I add more CPU cores, it ain't gonna do much. So you actually know your limits before you choose the type of EC2 instance to spend your money on. And this is a better fit of the coherency model. You could see the beta value is high and alpha is 0. So you know your requests are spending time coordinating with each other or doing crosstalk with each other. And that determines how your efficiency of adding more cores is going to be. So I did promise crystal ball and predictions, but I never did that. So now we observed some metrics and we made a model to fit with it. So what are we going to do with that? You can extrapolate. That's the idea of creating that model. So I know how my software performs with this level of concurrency or with this many number of cores. Now, what is it going to do when I increase it? That's where USL comes in handy. So I literally just called up this predict function with how much, at what level I want to predict that, and it shows me this. It's essentially, it's a little easier when you see it through the charts. The same linear curve we saw, I can extrapolate it, and because it's doing regression, you apply the model and you know where your throughput is going to be if you run it with 192 cores. With the contention one, you're already contented, and when you are at 192 cores, your throughput ain't going to be much. And it also shows you where your peak is. So after which there is no point adding extra cores. Same applies for the coherency model, and you can tell at where your peak is and at 192 what you're going to get. So a bit of a crystal ball, so that the title was not entirely untrue, but the idea of looking at it is not with this. The idea is to use it as a diagnostic tool. So you know how your system performs at a given state. Then you apply the model, fit it, and see where it goes. And then you see a different behavior. Doesn't mean it does mean the model is wrong, but not in the traditional sense. That's where you need to be. But your model predicted that there, and you are falling behind. Then you start to understand why you fell behind and what penalty cost your service to fall behind is the key we are going after. I'm going to continue. There are limits to USL and thinking in this way. Noisy data is a problem. I mentioned observing actual metrics from real service. That comes with this caveat that noisy data has nonlinear effects. So your model's not going to be entirely trustworthy with a lot of noise. Distributed systems are hard to model. You have this one endpoint that depends on 10 microservices. Good luck modeling the whole thing. I know it sounds funny that it applies to isolated one little thing, but in real life, isolating to that is a difficult task. Then there is asynchronous event-driven models. Now your arrival rate goes up the window. Good luck explaining that mathematically. I'm not going to try. So you have coherency factor, which is assuming one-to-one coordination. And that's why it was n times n minus 1. But in reality, that may not be the case. And you need to be aware of it before you make that model. And systems don't always behave the same way at scale. You have rate limiters that kick in at a certain throughput. You have dependencies that switch to a different algorithm when the traffic goes beyond a certain point. You need to kind of know your system before you model it and apply this. That's what this is. And oftentimes in our cloud world, we have noisy neighbors. So you can't take your numbers for granted. You need to identify such situations and account for it. So rate limiting and throttling at dependencies are to be factored in. This does not mean that USL is completely useless and you're going to throw it away and do something else. This means that USL still gives you an idea of, given your software's nature, where you could be, and you observe something different, then you know what the difference is and where it is coming from. So it's quite handy as a diagnostic tool. When you work with USL, remember that garbage in, garbage out. When you extrapolate to 192 cores like I did, don't go beyond 2x. It becomes crazy world. And another key thing is it's nice and fun game to maximize the throughput value. But in reality, that's not what we are all after. What we want is throughput at a certain desired latency. Now, I talked about little slow at the beginning of the presentation, and I did tell you that it comes in handy to do napkin math. This is the place where it comes in handy. So if you are looking at throughput and you want to relate it with response time, you have little slow. Apply it, and you have throughput at a certain latency, and you can apply it to USL as well. So with that, I just wanted to summarize a few things that I would like you to keep in mind after you walk away. Start thinking in queues. It helps to formulate your problem in queues so you can solve it much easier. Use Little's law as a fundamental relationship between throughput and response time and utilization. Use USL as a diagnostic compass to identify my service spends a lot of time with contention. My service is having coherency penalty. How can I improve it? How do I remove that bottleneck? Keep queuing theory in mind. Favor pooled resources over favor a single queue and shared pool of workers. Always attack variability. How do you attack variability? Use caches where it is reasonable, sensible, and possible, and use optimizations for slower code paths to reduce variability. What do I mean by that? Many times you have the same server, which is a processor, thread, whatever, handling a small request and a big request, or a light request and a heavy request. So what would help you is to just bin pack them. Have another service handle the easy work, and another instance of it handle the heavy work, which will improve your average response time. So if that was the only thing you took out of this talk, I would be happy. And heavily tailed service times, then consider priority queues or size-based routing. This sounds intuitive now after you think about them as queues, service times, and wait times. This is why it's important to apply the terminology that way. So heavily tailed service times, I suppose it is intuitive. If you have your service times distributions and you have some of them that spends 10 seconds in service while some that spend 0.1, then consider prioritizing ones and separate them away and have size-based routing. So these are the things that I could think of when I went to the workshop with Dr. Gunther and spending 4 days with the USL. So I'm hoping that you listen to this and then you have some idea and you start to question your own notions saying, oh, how do I do that? How do I do this? What would happen if I did that? So please play around and find your own solutions to the problems. Always feel free to reach out to me if you have an interesting problem. I'm happy to work with you and solve that puzzle as well. With that, thank you.